We previously developed the induced drag from lifting line theory and came up with this solution here where the induced drag depends on all of the Fourier coefficients squared. And that came from an analysis where we had the induced drag is equal to the integral from minus b halves to b halves of the local induced drag, or the section induced drag, as a function of z dz. And that section induced drag at any location z was equal to a rotation of the lift vector. It's actually the local lift times the sine of the induced angle of attack. And of course, the induced angle of attack, alpha sub I, was a function of gamma. And so we were able to plug that in there for alpha sub I, and lift actually is also related to gamma. It's from the Kutaijikowski law, rho v infinity times gamma at any z location. So this is lift at any z location. Anyway, we were also able to plug that in, and then plug this into there, integrate it, and we came up with this equation here for the induced drag. Well, when you're in a steady rolling rate, this changes just a little bit. This equation is still correct. The total induced drag is the integral of the local induced drag, but the local induced drag is a little bit different once the wing is rolling. I'm sorry, it doesn't have to be a steady rolling rate. Anytime the wing is rolling. And that is that not only is the lift rotated by the induced angle of attack caused by the downwash, but it's also a function of the rolling rate itself. Remember, if we go back up to our discussion of resulting yawing moment, we have this lift here is rotated by not only the induced angle of attack, but also the change in angle of attack due to our rolling rate. Remember, we have this kind of linear change in angle of attack across the wing due to our rolling rate. And so the angle, the local angle that is changed by is zp over v infinity. So we're actually going to put that in here. So it's going to be alpha I plus zp over v infinity. So and so when we now plug this in, so again, alpha I is a function of gamma, just like before, and lift is a function of rho v infinity gamma. And also one last thing that we actually do in both of these developments is we assume a small angle. So we neglect the sine and just simply use the angle here, alpha I plus zp, multiplied by the lift to get the induced drag. And when we do that and compute this induced drag coefficient over here, we actually get a new term that shows up, and that is that we get a minus pi times the aspect ratio over 2 times capital A2 times p bar. And remember, p bar is our dimensionless rolling rate, pb over 2v infinity. That's how we non-dimensionalize our rolling rate. But anyway, this is now our new induced drag relationship that includes the effect of rolling rate, and it depends on A2. It turns out that the only difference here is that we have an additional dependence on the second Fourier coefficient here, multiplied by p bar. Now, there's an excellent paper about this by Warren Phillips. I'll put a link at the bottom of this video to that paper, and he goes through this entire derivation and shows you what happens with each of these terms and how you walk through this process in order to come up with this equation here.